This is the brief on how we solve some really complex real-world heat conduction problems. So we're looking at a couple of sources here. One's a math guide, the other's more cross-disciplinary, and they both point to this really powerful technique for simplifying what are usually some pretty messy equations. You know, the ones that predict how heat flows in something like a metal rod. Okay, so first up, the real challenge here is that the problem is what's called inhomogeneous. What does that mean? Well, just imagine you've got an insulated rod, but its ends are held at fixed temperatures, and they're not zero. Because of that, the heat can't just, decay away to nothing. It prevents us from using our standard, simpler models. So what's the trick? This brings us to the second key idea. You isolate the steady state. You basically figure out what the temperature profile will look like after a really long time once everything's settled down. And it turns out it's just this simple, straight line of temperature from one end to the other. And finally, this is the brilliant part. We split the total temperature into two pieces, that steady long-term profile and a temporary decaying heat wave. When you mathematically subtract out that steady state, poof, the messy problem becomes a clean, simple one. It just models the decay of that initial thermal shock. So the total temperature at any moment is just that fixed profile with the temporary wave on top of it. So by isolating that stable, long-term profile, you can use simple decay methods to solve even super complex thermal systems.